Right, hello year 11. I'm currently doing this in the corridor just outside some lessons that are going on. So I'm going to keep my voice down a little bit, but let's start off with this. This is your mock Norton Doctor, that's my real name. Right then, so let's have a little look then. This was actually the 2025 paper, paper 1. So this is topics 1 to 5 from your GCSE. And we can learn a lot by going through these past papers, looking at the specifics that examiners want from us. Right, question 1 was done really not very well, although a lot of you know exactly where the non-metals are. What AQA want is towards the right of the periodic table and the top. So the right and the top of the periodic table. So they want this sort of idea that they're up here. Whether or not you agree with that doesn't matter. You have to say right and top. Gallium is a metallic element of group 3. I'm just going to pause here and go and get a periodic table, 1 second. And there we go. So gallium is a metallic element in group 3. Which of these properties is not typical of most metals? So metals have got high melting points, they conduct electricity, they're shiny, etc, etc, which is not typical this. Most metals have got a high melting point. Gallium melts below 100. So next, sodium atom. So I don't need my periodic table for this because it says a sodium atom is that's its atomic number. That means it's got 11 protons and 11 electrons. So a sodium atom, you needed to do 2, then 8, then 1. Make it nice and clear, please. Some people are a bit scruffy on this. 2, 8 and 1, very straightforward question. Mendeleev created an early periodic table. Mendeleev placed most of the elements in order of atomic weight. Remember, he didn't know anything about protons, neutrons or electrons. Tellurium and iodine were not placed in order of atomic weight. Why didn't Mendeleev not place tellurium and iodine in order of atomic weight? Well, here they are actually on the periodic table. Here's tellurium and iodine, and you'll see they are not in order of what we now call relative atomic mass. Mendeleev swapped their groups so that their properties most closely represented the group that they were in. So he swapped them based on their properties, so their properties matched the group they were in. And you had to really specifically say that they matched the group that they were in. You could say so that iodine matched group 7 or the tellurium's properties, matched group 6. But it had to have that idea in matching the properties, so we needed this, properties of the group. Some people in this class kept misusing the word, saying the wrong word instead of properties. You said things like characteristics. Please, this is the chemistry word, properties. Argon is an element of group 0 in the periodic table. Why is it unreactive? Okay, it has a full outer shell of electrons. I prefer it when you say of electrons, not just a full outer shell. So it is stable electron structure. You could have said a stable full outer shell of electrons for 2 marks. So one idea that the electron configuration is stable and one that it's a full outer shell. They are 2 points for the 2 marks. A lot of people only scored 1 mark on there. Alright, instead of stable electron structure, a few of you got the answer, the idea that doesn't gain or lose, or share electrons, but a lot of people got the 2nd mark for that. Okay, full outer shell alone wasn't enough. It's unreactive because it doesn't want to gain or lose electrons because it's got a stable full outer shell. Isotopes, I don't know how many times I can say this really. You've got to learn your definition of isotopes because it comes up every year. I'm going to give you an example of isotopes. Chlorine, these are 2 versions of chlorine. This is 35 and 37. Right, what in terms of subatomic particles? 17 and 17, that means they've got the same number of protons and electrons, but a different number of neutrons. you had to talk about the subatomic particles, protons and electrons and neutrons. Just learn it, will you? Right then, table 1 shows the mass numbers and percentage abundances of the isotopes of X. So you've got an isotope of X that weighs 113, and you've got an isotope of X that weighs 115. This is 4% abundant, this is 96% abundant. So you know if you were to get a sample of X, it's mainly going to weigh 115. 96 out of every 100 weigh 115, and a few of them weigh 113. So my best guess on this, I mean, I could very easily do the calculation, but really you can see that X is going to weigh about, that means about 115. A sample of X is going to basically weigh 115 because it's nearly all isotope 115. That was a very straightforward question. This is an ionic compound, so we know we're dealing with M-cephalobochylad, more on that later. We're dealing with an ionic lattice that goes plus, minus, plus, minus, plus, minus, and it asks you to look at this diagram and determine the empirical formula. This question has come up quite a few times over the years. So just to remind you of this, if you get a crystal of salt, like a crystal of salt like that, it will have millions and millions and millions and millions of sodiums and millions and millions and millions and millions of chlorides, but we just write NaCl. Because with ionic compounds, what this formula represents is the simplest ratio of one ion to the other. That's what an empirical formula is, the simplest ratio. All I'm going to do then, I'm going to count up all of the S's. 1, 2, 3, I'm going to make sure I tick them. 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 S's. Calciums, 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 calciums. Empirical formula means simplest ratio, CAS. If there are 9 to 9, there'll be 90 to 90, there'll be 900 to 900. There's 1 to 1. That's what that meant. The examiner's report on that was fine. You wouldn't be allowed SCA because it gives you calcium sulfide. It tells you the order to write it in. I don't know whether I gave you benefit of the doubt for SCA, maybe. Okay, calcium is in group 2 of the periodic table. There it is. Calcium is in group 2. That means it's got 2 electrons in its outer shell. Okay, I'm just going to draw the outer shell like that. Sulfur is in group 6 of the periodic table. That means it's got 6 electrons in its outer shell. Looks like that. There's a calcium atom, just the outer shell shown. There's a sulfur atom, just the outer shell shown. Describe what happens when a calcium atom reacts with a sulfur atom. Alright, calcium will lose 2 electrons, these 2. Sulfur atom, calcium atom loses 2 electrons. Sulfur atom gains 2 electrons. I like you then to say they were transferred from a calcium atom to the sulfur atom. I know it's been implied here, but I would like it said. One loses, another atom gains. What this means is the calcium forms Ca2 plus ions. If you lose 2 electrons, you become 2 plus. Sulfur forms S2 minus ions. Something very specifically, now just check yours that you've done this. If you've just written that calcium loses 2 electrons, no, you are allowed it on this, but I would be careful. It does say on the mark scheme here, I'm reading it to the side, calcium loses electrons, sulfur gains electrons. 1 mark, 1 mark. I would prefer calcium atoms lose 2 electrons, sulfur gains 2 electrons. Some reference to transfer of 2 electrons here, and then calcium forming 2 plus, sulfur forming 2 minus for 1 mark. You could just write calcium forms positive and sulfur forms negative and get the mark for that. But I would prefer this. You're all very, very able students. This should be very steady. Most people scored 3 or 4 out of 4. Right, structure and bonding of graphite questions are often quite tricky because it's difficult to know how deep to go. But please, it does not ask for properties. So please please do not talk about whether it can conduct electricity or whether it's slippery. It didn't ask. That's why it's only 4 marks. Okay, so what have we got here? Sort of indicative content then. So I would say each carbon atom covalently bonded to 3 others. Shows you this in the diagram. Each one covalently bonded to 3 others. It forms layers of hexagonal rings. There you go, there's a hexagon, there's a hexagon, there's a hexagon, and the whole thing is a layer. What else would I write? Giant covalent structure with many strong covalent bonds in a lattice. That's straight from our notes. It has delocalized electrons, 1 per atom, and a lot of people went into some lovely detail about this delocalized electron that wasn't involved in bonding. Some people said there is a delocalized electron, 1 delocalized electron per carbon atom. Read your notes carefully, please. So things that it says, you get 1 mark for saying a giant structure, 1 mark for saying layers. Hexagonal rings is all part of that as well. That's a good marking point. I'm reading the mark scheme as I'm doing this. Each carbon atom forms 3 bonds, was a relevant point. It's got delocalized electrons, 1 per atom. Weak forces between layers was also allowed. So 1 mark for saying strong covalent bonds, 1 mark for saying lattice. So all of those ideas were in there. If you wrote things that were incorrect, though, you didn't get any credits, of course. Substances that consist of small molecules do not conduct electricity. Notice they say small molecules, that is simple molecular as well. So we've got simple molecular, weak intermolecular forces, low melting points, don't conduct. That's from our table. So why don't simple molecular substances conduct electricity? Because I would say there are no charged particles that are free to move. Or you could say there are no ions that are free to move. Or there are no delocalized electrons that are free to move. This part of our table here is the least well known. Why don't they conduct electricity? Because they don't have delocalized electrons or ions that are free to move. In your notes, we have summarized it as they have no charged particles that are free to move. Okay, next one then, polymers. Now, I've done a little bit more on polymers recently, so this was a fairly tricky one. Polyethylene, well, from our second paper, this is an addition polymer of ethene. I'm just going to draw ethene there, by the way. So polyethylene, just may as well do a little bit of practice. Looks like this. And it will form very, very long chains of molecules. Why does polyethylene have a higher melting point than methane? Well, methane is a simple molecular substances with weak intermolecular forces. It's a very small molecule. Polyethylene is a very large molecule. It's a very large molecule with stronger weak intermolecular forces. So, polyethylene has more covalent bonds to break. Not that, because we don't break bonds, covalent bonds when we melt simple molecular substances. Polyethylene has no intermolecular forces to overcome. That's not the truth. Polyethylene has stronger covalent bonds. We don't break covalent bonds when we melt methane or a polymer. Polyethylene has stronger intermolecular forces. It was that one. There is a general thing here. Bigger molecules, so when we're in the world of molecules with weak intermolecular forces, bigger molecules have stronger whiffs, therefore higher boiling points. You've seen this with fractional distillation. Bigger alkanes, higher boiling points. Next, this question is about metals and metal oxides. Which substance is reduced in this reaction? So of course you have this. Oxidation is loss of electrons, reduction is gain of electrons. But this is asking us in terms of oxygen. All right, answer in terms of oxygen. A lot of people knew the answer here, but you got caught out on a technicality. Reduction is when you lose oxygen. So the substance that lost the oxygen was tin oxide, not tin. I know technically you're saying, oh, it's the tin that lost the oxygen, but we don't do that in chemistry, and maybe I wasn't specific enough. The tin oxide was reduced to tin. Reason, it lost oxygen. Okay, that's it. So a lot of you, that's not more revision, that's just going, oh right, it was the tin oxide and not just the tin. So for example, if carbon dioxide becomes carbon, the carbon dioxide has been reduced, not the carbon has been reduced, for example. Okay, why can carbon be used to extract tin from tin oxide? In other words, why does this happen? Because carbon is more reactive than tin. Or tin is less reactive than carbon, whichever way you want to do that. So most people got that right. Next. All right. Atom economy for the production of cadmium. I'm going to teach you the way that we've done it. I'm going to draw the fried egg like that. Cadmium weighs 112. That's 112 in there. Carbon monoxide weighs 12 plus 16, which is 28. So it's 112, it's the yolk divided by 112 plus 28, which is 140. So it's a 112 divided by 140 times 100, and the atom economy is 80%. Okay, next. Tungsten is a transition metal. What do we know about transition metals? 4 C's. They form catalysts, they're colourful, they form colourful compounds, they have multiple different charges, 3 C's. Potassium is a group 1 metal, so when we did transition metals you had to be able to compare the properties. Transition metals are harder, more dense, so they are denser. Transition metals are less reactive. Okay. Give 2 differences between the properties of tungsten and the properties of potassium. Okay, I would say tungsten is harder, tungsten is more dense. Okay, there's 2. There's lots you could do. You could do less reactive. You could say, well, that'll do. Yeah, that'll do. What I was going to say actually, melting points. Tungsten's got a higher melting point. Transition metals have a higher melting point. This is very steady. You just need to know transition metals against group 1. Tungsten oxide reacts with hydrogen to give tungsten and water. The law of conservation of mass states that the mass of products equals the mass of reactions during a chemical reaction. This answer was done really, really well by you lot, so well done. Basically, if you add up all of the MRs on this side, you get an answer of 238. The total MR is 238. The total on this side is 238. Okay, so that's what everybody did. As long as you're seeing 238 becomes 238. For those who didn't get that, sorry. WO3 is 232. 3H2 is 6. Add them together, you get 238. Tungsten is 184. 3H2Os is 3 times 18. And I promise you that also equals 238. So that was very straightforward. The reaction producing tungsten has a high atom economy. Why is it important to use reactions with a high atom economy in industry? Alright, so what atom economy tells us is that of the atoms that you put in, how many of them end up in your desired product. So this would be our desired product here, tungsten, and these are what we can describe as waste product. We weren't setting out to make water, so this is our waste product, not wasted product, our waste product. So it's important to use reactions with a high atom economy to minimize waste products. All right. Now, something else you could have written, you could have said anything about economic reasons. All right. You could have said ideas around it's wasteful in terms of money. You're wasting atoms, so you're making waste products. So it does say on the mark scheme, allow for economic reasons. All right. I like the idea of these. The idea of waste products. This was weirdly badly done. The elements of group 7 of the periodic table are known as the halogens. By the way, you should know that fluorine is a gas, chlorine is a gas, bromine is a liquid, and iodine is a solid. What you're asked to do then is predict the boiling point of chlorine. So I'm just seeing a bit of a trend going here. So I would imagine it looks fairly symmetrical. Something like that. Now it doesn't ask me to draw it on the graph, but I'm going to go with about -50. Something like that, in that region. You were given a window from -20, which is from here, down to -70, which is here. Alright, the idea is it's going to be symmetrical. So I'm putting it there, -50. Again, you were allowed in a range of -70 to -20. I had loads of you putting positive numbers in there. I don't understand what you've been doing. I don't get it. What is the state of fluorine at -250? Right. Fluorine melts, its melting point is -220. So colder than -220, it's going to be a solid. Alright. I'm just going to write this on. Melting point 220, -220. Boiling point is -150, 60, 70, 80, 85, 185, -185. I'm going to draw this on here. So when you have things that have got melting points and boiling points, they become a solid, a liquid, and a gas. Fluorine's numbers, it melts at -220 and it boils at -185. And you are asked, this is a very useful technique by the way, you are asked what is the state at -250. So I look at these numbers and go, oh, -250 is going to be in here, it's a solid. If I said what's its state at -200, -200 is between these, it would be a liquid. If I asked you what is it at 0 degrees C, 0 degrees C is up here, it's going to be a gas. This technique, very useful. Right, what's the number of electrons in the outer shell of an astatine atom? Astatine is in group 7, so the answer is 7. Hydrogen reacts with astatine to form hydrogen astatide. Predict the formula of hydrogen astatide. That will be HAT. I got a lot of people saying ATH, which you got the mark for, but record it in the way it says, hydrogen astatide, HAT. You might think, well, how am I meant to know that? Well, you know that hydrogen chloride is HCl. You know that hydrogen forms H pluses and chlorides form Cl minuses. So there's lots of ways to come up with this. Group 7 elements like to form 1 minus. Hydrogen is 1 plus. You could do that. Another way of doing it, you've drawn actually covalent molecules of these. This is probably a better way and makes more sense. But anyway, HCl is a molecule that you need to know, so HAT would also work. Right then, we're getting there. 22 minutes in, I'm on question 4. Explain the trend in reactivity of the elements going down group 7. So straight away, I'm in with this, SDAE. Right, as you go down group 7, atoms get larger. More shells. More electron shells. Size, done. Distance. So the distance between the nucleus and outer shell increases. There's the nucleus, there's the nucleus, there's the nucleus, there's the nucleus. The distance between the nucleus and the outer shell increases. Distance. A is attraction. So the attraction between the nucleus and outer shell electrons decreases. Attraction done. So an electron is gained less easily. Gained less easily. In group 7, they've got 7 electrons. They like to gain an electron. SDAE. Very poorly answered by most people in the country. Fairly well answered by people in this class. Okay, a more reactive halogen can displace a less reactive halogen from a solution of its salt. Write a balanced equation for the reaction between bromine, which is Br2, and potassium iodide, which is Ki. Now, you're not told the formula for Ki, it's just expected that you know potassium iodide is Ki. Bromine, Br2, potassium iodide, Ki. What's going to happen? Bromine will displace the iodine, so I'm going to make KBr and I2. They're going to swap places. I've now got 2 iodines over this side. I'm going to need 2 of these, and I'm going to need 2 of these to balance. 3 marks. 1 mark for the correct bromine into iodine, 1 mark for the correct Ki to KBr, and 1 mark for balance. Next question. Describe the plum pudding model of an atom. I'm going to draw it. That is a positive sphere, or a sphere of positive charge, or a ball of positive charge with negative electrons embedded, or you can say inside it or scattered inside it. But if you say a ball of positive charge or a sphere of positive charge, 1 mark, with negative electrons embedded, you get both marks. The model of the atom changed after the alpha particle scattering experiment. 2 conclusions that were made from the alpha particle scattering experiment. Remember, that was gold foil. Most of the alpha particles went straight through. So the atom is mainly empty space, and there is a nucleus in the center which is small, very small, compared to the size of the atom. If you just said there's a small nucleus, I'm afraid that's not enough. Of course it's small, we're talking about atoms. It's very small compared to the size of the atom. Or you could say that the nucleus is positively charged. So what they discovered was a positively charged nucleus in the center of the atom. Niels Bohr made another change to the model of the atom. What was this change? This is about learning. Learn this. He said that electrons orbit the nucleus in shells, and these shells were at specific distances from the nucleus. You can't just say he discovered electron shells. This is a biggie. Electrons orbit the nucleus in shells. Alright? You can also say, because it's physics, you can say electrons orbit the nucleus in energy levels at fixed distances. Next, a helium atom has a radius. A helium atom has a radius of 1.4 times 10 to the minus 10. The nucleus is 1.7 times 10 to the minus 15. If you divide the bigger number by the smaller number, you will find that it goes in 100,000 times. I haven't got my calculator with me, I'm afraid. So, right, calculate the simplest surface area to volume ratio. If you're asked to do surface area to volume, please record it as surface area to volume. You put the surface area there and the volume there. Now, what the examiner wants really is a ratio to 1. Okay, anyway, the surface area of here, there are 6 surfaces, and each surface is 1.2 times 1.2. So there's one surface there, there's another there. So each surface is 1.2 times 1.2, that's working out an area, so 1.2 squared. And then there are 6 of them, so times 6. I was looking for this number, 8.64 nanometers squared. I was just looking for that number for the surface area. The volume of this is 1.2 times 1.2 times 1.2. The volume is 1.2 to the power of 3, which is 1.728 meters cubed, nanometers cubed. I was looking for this number and not bothered about the units. So I've now got a ratio of surface area to volume. Don't flip these round. I don't want volume to surface area. 8.64 to 1.728. 8.64 to 1.728. If you divide both of these by the smallest number, 1.728, 1.728, you end up with this ratio. Of course, that divided by itself is 1, and this is 5. If you wrote, instead of 5 to 1, 1 to 5, there's an easy fix for you, isn't it? Just do what's asked, surface area to volume ratio, not volume to surface area ratio. Alright, nanoparticles question. Now, we haven't covered much about nanoparticles, I'm afraid, apart from the fact that they have a higher surface area to volume ratio. The examiner asks you, why do we use nanoparticles? Nanoparticles seem to be, people say that they are better because they have a higher surface area to volume ratio. So you need less to, you need less of the product to be able to, in this case, coat the glasses. If they've got a higher surface area to volume ratio, you need less of the substance to be effective. Okay? There was also this idea that some of you hit upon, that if you're using nanoparticles, that means that more light would get through the lenses, so they would work better as glasses. If you had a thick layer of particles on the surface of the glasses, you wouldn't be able to see through the glasses. So some people just thought logically about that and got a good answer. But this is the general answer for nanoparticles. If you look at nanoparticles, what do students need to know? Nanoparticles have a very high surface area to volume ratio, so you need less of the substance to do what it's designed to do, to be effective. In this case, this was to coat the glass. Alright, I'm going very fast, of course. Aluminium oxide is an ionic compound. So what we have to say now is M-cefabocylad. Okay, so we know that they've got high melting points. They conduct electricity if they're molten or dissolved. Right, Daniel? And they have a high melting point, and they're MC-bocyl in the past. Well, now it's M-cefabocylad. Why have they got a high melting point? Because they've got many strong electrostatic forces of attraction between oppositely charged ions in a lattice, acting in all directions, which require a lot of energy to break. Because you have to say why it's got a high melting point, which require a lot of energy to break. Name the substance. Right, okay, so this question is about the electrolysis of a molten mixture, and it was aluminium oxide. So this is specifically aluminium electrolysis. Now, my daughter in her school, they said they've never heard of this. They've not even been taught it, so what an advantage you've got. What substance is added to aluminium oxide to form a mixture? All right, it says up here, aluminium is extracted by electrolysis. The mixture contains aluminium oxide and another substance. It is cryolite. Cryolite is added. I told a really blooming good story about this, so I hope you remember it. Okay, so I'm not telling you it again. So you add you mix it with molten cryolite. Give one reason why the mixture is used as the electrolyte. It lowers the melting point. Okay, lowers the melting point. That means you need less energy, so it saves you a load of money. Oxygen is produced at the positive electrode. So again, just if you didn't do well on this question, look in your notes at electrolysis of aluminium. All right. So what happens when you electrolyze aluminium oxide is the oxide ions do this, and they produce. It says they produce oxygen. Well, oxygen is O2, and you've only got one other space there. If you've got O2, that means you needed two of these. Now I'm looking at this half equation. There are two minuses, so that's 4 minus on this side, so I need 4 electrons on this side. Again, if you're unsure about this, I've got some videos on writing half equations for GCSE that I did for you lot. The positive electrode must be continually replaced, yes, because here are the positive electrodes dangling into the molten cryolite. They are made of carbon. You could have said graphite. All right, because oxygen forms there, the carbon reacts with the oxygen to form carbon dioxide. Carbon reacts with oxygen, 1 mark, to form carbon dioxide. All right. You could have written this, C plus O2 makes CO2, would have got you all the marks for that bit. They're made of carbon, you have to say that separately. Carbon reacts with the oxygen to form carbon dioxide. Next question. Quite close to the end of this, I'm going to have to save this shortly. Right, this question, evaluate. Evaluate means we've got to reach a judgment, which a lot of us didn't. The examiner's report was very scathing of this, said hardly anybody scored more than 1 mark, and that was the case. Hydrazine is a compound of nitrogen and hydrogen. Scientists are researching the use of hydrazine in fuel cells. A fuel cell is where you generate electricity by doing a chemical reaction in a special cell. Table 2 gives some information about the use of hydrogen and hydrazine. So whenever you're given an evaluate question in a table, you need to talk about each of these rows first and then reach a conclusion. All right, so if I want to use these in fuel cells, it means I'm going to be carrying this fuel, maybe in a car or something, and I'm generating electricity. So I need to talk about what each of these rows. All right, so hydrogen is a gas at room temperature. Hydrogen is a gas, hydrazine is a liquid. Liquids are easier to store than gases. I've done that. Okay, so at the minute, hydrazine is winning because liquids are easier to store than gases. Hydrogen is explosive and hydrazine is toxic. Now, they are both bad things, so I'm not going to reach a judgment. These are both dangerous substances to be handling. I would write that. Explosive versus toxic. Some people are trying to tell me that toxic is worse than explosive or explosive is worse than toxic. It didn't want you to do that. Explosive and toxic are both bad for fuels. In the equations, what can I see? Well, this produces water, this produces nitrogen and water. All of these, they both produce safe or unreactive products. Some people are trying to tell me that nitrogen's bad for you. It is 78% of the air that you're breathing. It is not bad for you. So they both produce safe byproducts. Okay? So you're allowed to say that, and you should. Anybody who tried to tell me that these products are worse was wrong. The voltage produced in volts. Okay, a hydrazine fuel cell produces more volts per cell. And that means that you're going to need not as many cells to do the job. So that's going to be beneficial in terms of like weight of the cells in your car or your vehicle. Now that was tricky, but you couldn't just say it produced more. You weren't just allowed to say this number is bigger than this. It produces more, so that means you don't need as many cells to power your device. This was often got by lots of people. Hydrogen needs a platinum catalyst. Hydrazine does not need any catalyst. Platinum is very expensive, so maybe hydrazine wins that. Okay, so liquid, catalyst not needed, produces more electricity, safer products. I think a good judgment would be hydrazine is better for a fuel cell because overall it's going to be cheaper to run and it's easier to store. Alright, so I made sure that I made a judgment. So did you notice I said something about this? I didn't just quote the table, I didn't rewrite the table. It was like, this is a gas, this is a liquid, so. This is explosive, this is toxic, so. This is 1.23, this is 1.61, so. This is platinum, this is... Okay, that's a good way to do any evaluate question, as long as you make a judgment at the end. No judgment, you're never getting over 2 marks. Right, what does this show? This is a model of a molecule, a simple molecular substance. Each of these sticks is a bond, a covalent bond. So what I'm seeing here, there are no double sticks. These are all single covalent bonds. They're all dot crosses like that, shared pairs of electrons. So what I need to do, between the nitrogens, there's a shared pair of electrons. Nitrogen to hydrogen, shared pair of electrons, shared pair of electrons. I'm just going around like this. Okay, so all single bonds. Now I need to just make sure that everything's got a full outer shell. Nitrogen, I'm going to count these. 1, 2, 3, 4, 5, 6. You need 2 more electrons out here. 1, 2, 3, 4, 5, 6. You need 2 more electrons out here. 2 marks. A few people missed that question out. Give one advantage of the ball and stick model. The ball and stick model throws it in 3 dimensions. Okay, but the dot and cross diagram does not. The dot and cross diagram is just 2-dimensional. Alright, this question then, I wanted to see it like this. Bonds broken and bonds formed. Alright, this is something that you really do need to make sure that you can get. To break everything on this side, you're going to break 1, 2, 3, 4 of those. That is 4 times 391. You're going to break an NN, and we're trying to find out that. So you're going to break X. You're going to break an OO, which is 498. If you add up all of this side, you get 2062 plus X. This is bonds broken. Bonds formed. Sorry about the scruffy writing. You're going to make an N triple bond N, which is 945, and you're going to break 1, 2. There's 2 times 3, 4. 4 of these. 4 times 464. So this side here is 2,801. That would get you a mark. And that would get you a mark. I also know that this value is 581, the energy change. So the energy change, the difference between these 2 values. So I would say that 581, the energy change is the bonds broken minus the bonds formed. 2062 plus X. Energy released minus... I've messed that up a little bit. So 2801 minus 2062 plus X. Now a lot of people manage to do that in various different ways. You can then solve for X and you get a value of 158. That was garbled. If this was you and you don't know how to do it, please come and see me. Alright, but the answer was 158. What is the formula of the ion that all alkalis contain? Alkalis is OH minus. That was forgotten by a lot of people. A lot of people went for H plus, which is obviously acid. Come on. Right. They're doing a titration. This is triple science only. Issues that they used in there as well. They used universal indicator. Now, rather than universal indicator, you could use phenolphthalein. Phenolphthalein gives you a sharp colour change. Okay, a sharp colour change. Universal indicator does not. It gives you a range of colours. So any idea that phenolphthalein is a sharp colour change? You could also have used a pH probe. Okay, it would give you like a clear indication of when it's pH 7. A second improvement could be add the sodium hydroxide drop by drop. You can also say drop-wise. And the reason for this is you get a more accurate end point. So they like this idea, end point on there, more accurate end point. You could also say things like rinse your equipment with the chemicals that are going to go into them, but these are the best ones, really. You didn't get any mark for saying read to the bottom of the meniscus, I'm afraid, although a lot of you did suggest that, but it wasn't a good enough improvement. Right, a lot of people overcomplicated this. If this is 24 and this is 25, anywhere between 24 and 25 is a number between 24 and 25. There's 24 and a half. There's 24.1, 2, 3, 4, 5, 6, 7, 24.7. It really is that simple. I saw all sorts of calculations on here. You're just reading that. It is a line between 24 and 25. That is very, very straightforward. So a lot of people overcomplicated that idea. Right, calculate the concentration of the sodium hydroxide solution. I'm going to stop there. That is the first 40 minutes of this test. I'm very nearly done. That is that.